Alright. So in this example problem, we're asked to determine the internal normal force, the shear force, and the moment at points D and E within this handbrake assembly. So we have a point D is located on the member AB, and point E is located on member BC. Okay? So to solve this problem, we first need to solve for our reaction or unknown forces within our members. So to find the unknown forces within our members, we need to draw our free body diagrams of our two components. So we need to draw our free body diagram of BC, and we're going to draw our free body diagram in a second of ADB. Alright, so we're going to start off with the free body diagram of BC. So if we look at BC, we know that it's at a 60-degree angle relative to the negative x-axis. Here we know that it has at point C, we know that it's a pin joint, so we can assume for that pin joint that it'll have some magnitude C, and it'll be at some angle theta. Alright, there's no applied forces along the length of the section, and we do know that at the other side of the member at point B, we also have a pin joint, so we'll say that at point B we'll have another force, and we can say that force acts relative to the x-axis by an angle theta b. Okay. So since there's no other known forces in the system here, and I guess I should put in member E here. We know that member point E is 0.75 meters from point B. Alright, but if we look at our free body diagram, we have only two forces are being applied. To BC. Alright, since this is true, what we can say is we can have one, we know, since there's only two forces, we know from that, we know that force C, the magnitude of force C is equal to the magnitude of force B, and we know that they are going in opposite direction, and we know that they are going along the member length, so they're going along the direction of BC. So from this information, what we're going to do here is we're going to simplify this down to being force B and force C Alright, they're going to go equal and opposite. So we'll say that B is equal and opposite. And we know that they both will be it'll be 120 degrees from the positive x-axis. So that's how they will act. Alright. So because there's no known forces that are being applied to BC right now, we can't solve for the magnitudes, but we do know that this relationship is true. So our next step here is we're going to draw the free body diagram of ADB. Right, so we know that member ADB goes along the is at a 30-degree angle relative to the relative to the horizontal. All right. So we know at point A we have a pin joint. All right, and then at point B we know we have a pin joint as well, and we know at that pin joint it will apply an equal and opposite force as is applied to BC. So I'm going to draw this force going up. All right, and we know that this angle between force B and the member is at a 90-degree angle here. All right, and then we know that 3/4 of a meter down from point B, we have an applied force of 60 newtons. All right. So since we know we have a I'll call this theta A, and I'll call this A here. We know that we have 1, 2, 3 forces acting on member ADB. All right, and we know since we only have 3 forces, ADB is a 3-force member. So we know for that to be true, all forces must act at a single point, or not single point, but go through a single point, or they must be parallel with one another. So in this case, we already have force B is parallel with the 60 Newton force, so force A will also have to be parallel with the 60 Newton force. So what we're going to do here is just going to redraw force A. All right, we're going to say force A will be at a 90-degree angle relative to the surface here, or to the member. All right, so I'm going to get rid of those two notations here. All right, and that's our updated free body diagram because we know it is a 3-force member. All right, so so what we can now do is we're going to define our coordinate system to make our life a little bit easier. So instead of having our traditional x being on the horizontal and y being on the vertical, we're just going to rotate these 30 degrees counterclockwise here, just to make our mathematical lives a little bit simpler. So we do know to find out our moment arms, we do know that this horizontal distance from point A to point C is 2 meters. We know the rest of the angles of this internal triangle. So what we're going to do now is to find out force B. We're going to sum our moments about point A and set that equal to 0. Alright, so to do that, we'll end up getting we'll get the magnitude of force B times the length from point A to point B minus 60 newtons times the length from point A to where the force is being applied. Call this point F. Alright, so that's going to be equal to the magnitude of B times 2 meters cosine of 30 degrees minus 60 newtons times 2 meters cosine of 30 degrees plus 0.75 meters. If we rearrange and we solve, what we'll end up getting is we'll get the magnitude of B is going to be equal to 60 newtons times the 2 meters cosine of 30 degrees plus 0.75 meters divided by 2 meters cosine of 30 degrees, and we'll end up getting 85.981 newtons, which we round to significant figures, ends up being 86.0 newtons. Right. So if we plug in, if we look back at our other free body diagram here, we know that the magnitude of C is going to be equal to 86.0 newtons as well. Alright. So if we now now we can solve for force at A. Alright, so the force at A to find the force at A, what we're going to do is we're just going to sum all of our forces in the y direction and set that equal to 0 on this diagram. And what we'll end up getting is we'll get A, the magnitude of A, plus B, the magnitude of B, minus 60 newtons. So we'll end up getting A will end up equaling 60 newtons minus 85.981, and after we round for significant figures, we end up getting minus 26 newtons, 6.0 newtons. Cool. All right. So with this information, what we're going to do now is we're going to take a couple of section cuts. So we're going to take a section cut from point D to point F. So what this will look like here is we'll have our section cut at D. Alright, and then this is at a 30-degree angle here. We will have our applied force B, which is equal to 86 newtons. And then we have our 60 Newton force going down. Alright, and then at point D, where we took our section cut, we have our three internal forces. We'll have ND, you will have VD, and we will have the moment at point D. Alright, so to find each of these internal forces, we're just going to apply our equilibrium equations. We're going to set our x and y axes. That's our x-axis being along this the section, and our y-axis being perpendicular to the section. So if we do that, we can we'll sum all of our forces in the x direction and set that equal to 0. If we do that, we will get just minus ND. Therefore, we can say that the normal internal force at point D is equal to 0 newtons. If we then sum the forces in the y direction and set that equal to 0, we'll end up getting 86.0 newtons minus 60 newtons plus VD. So we'll end up getting VD is going to be equal to minus 26.0 newtons. Alright, and then the summer moment about point D, so that equal to 0, we'll get minus md plus 86.0 newtons times 1 meter minus 60 newtons times 1.75 meters. So we would get MD is going to be equal to minus 19.0 Newton meters. So once we have the internal forces at point D, we can then solve for the internal forces at point E. So what we're going to do is we're going to take a section cut at point E. So we'll draw our section here. So we have our internal force B and our section cut at point E, which we know is 0.75 meters from point B. We have we'll have NE, we will have VE, and we will have our moment at E. Okay. So if we treat this, we'll have our y-axis here and our x-axis here. So if we sum all of our forces in the x direction and set that equal to 0, we'll end up getting minus VE as being our only force. So therefore we can say that VE will be equal to 0 newtons. Alright, and then if we sum all of our forces in the y direction, set that equal to 0, what we'll end up getting is we'll get minus B plus, minus NE So we'll get NE is going to be equal to minus B, and we know that B is equal to 86.0 newtons, so we should get minus 86.0 newtons here. And then if we sum all of our moments about point E and set that equal to 0. Alright, the only thing we have is we only have a single couple moment, ME. Point B goes through point E, so it doesn't create a couple moment. So ME would also be equal to 0. Alright, so to summarize what we've done in this problem is we had a two-member machine that we broke down into its two members, ADB and BC. So we drew our free body diagrams of both of those members. We recognized that member BC was a two-force member, so we were able to highlight that, or say that point B and point C needed to be parallel and equal in opposite direction, and they had to go along the member BEC. Then we drew the free body diagram of ADB, and we recognized that force A had to be parallel with force B and the applied force. Alright, and then using the equilibrium equations, we could solve for our unknown forces at our joints. So we were able to solve for force B first, and then we could solve for force C from that, and then we were able to then solve for force A. Once we had all of our unknown forces, we then just had to take our section cuts of our two sections. So we took a section cut from point D to point F. You could have also taken a section cut from point A to point D. So you would have just had to include your applied force here, and then you would have had equal and opposite forces, internal forces at point D. Alright, and then you just use, either way you took the section cut, you could then solve for ND, VD, and MD. You will get the same answer regardless of how you took the section cut. And then at section E, you could do the same thing. It didn't matter which way you cut the section. You could have cut it this way as well, where you had force C acting on the bottom of it, and then you would have had NE, and you would have had VE, and you would have had ME. Alright, and again, all of these internal forces are opposite each other on the section cut, and you would have gotten the same answers for NE, VE, and ME if you took the section cut this way. Alright, so that concludes this problem on how to find the internal forces within a machine.